we continue with our treatment of extrema of functions in the second part of this lecture. So we had set up the idea of local extrema. Now we talk about absolute extrema or global extrema. So if f has domain D, we say f of D is the absolute maximum value or global maximum value of f on D, provided that f of D is bigger than or equal to f of x for all x in the domain D. So this is the kind of situation like, say, y equals 1 minus x squared. If we look at this function, its domain is the whole real line. We can plug in any x. And it has an absolute maximum value here at 1. It's the largest value that this function attains. It does not have a global minimum value or even a local minimum value. Similarly, the other way, we have an absolute minimum or a global minimum value, f of c, as long as f evaluated at c is less than or equal to f of x for all the other valid x that can be fed to f. So for all the x in its domain. Now that we have this idea of looking at a function and recall we had said points where the tangent line is horizontal, that gives us the set of points where we could have local maximum values or local minimum values. Remember that it's a necessary condition that the tangent line has to be horizontal at any extreme point of f. We call these types of points critical points. So remember, because we have a theorem that says at any local extrema it has to be the case that the tangent line is horizontal for a differentiable function. That means if we want to find local extrema of f, we need only find the points where the tangent line is horizontal or where f prime is equal to 0. That gives us the set of candidates for possible local extrema. We also say if you have a place where the f prime doesn't exist, we include that in this definition. Those two types of scenarios, points that satisfy either of these conditions, we call critical points of f. And critical points are types of points we will focus on extensively going forward. And the reason why is this is one of the reasons why, this theorem here. So we're coming back now to the case where we have a function that is continuous on a closed interval. So suppose that f of c is the absolute maximum. This also works for minimum, but let's concentrate on maximum. Suppose that f of c is the absolute maximum value of the continuous function f on closed interval ab. Then c is either a critical point of f or one of the endpoints. Recall that we had the result that if you have a function that is continuous on the closed interval ab, which means we can draw, when we draw the function, we start here, and I can't take the pencil off the paper. We had noted, we had a theorem that said such a function attains a maximum value on AB, and it also attains a minimum value on AB. We saw that it could occur at the endpoints. In this picture, we see this has its minimum at the left endpoint x equals a. But notice that its maximum occurs here at this peak. But what do we also notice about that maximum? It happens at a point where the tangent line is horizontal. It happens at a critical point of the function f. And when your function is differentiable on a closed interval AB, then these are the types of points where you can have a maximum value or a minimum value. If the function is just continuous, then note when it's not differentiable, those points are also included as critical points. But the key thing to recognize here is that if you have a maximum value occurring at a point C on the interval AB, then C is either an endpoint or a critical point. Either the derivative is 0, so you have a horizontal tangent line, which is picking up on the top of a local max value or a local min value, or you have the derivative not existing. Point is, it has to be the case that this is happening at either a critical point of f or an endpoint. We do the proof. This is a pretty quick proof. If C is not an endpoint of f, of AB, then f of C must be a local extremum of f on the interior. It still is, after all, the absolute maximum value. So if it's not happening in an endpoint, if it's the absolute maximum, it's also a relative maximum. If it's a local extremum, then f prime of C equals 0, or f prime of C does not exist, which is what we wanted to show. It's a critical point. That's what these two conditions define. So this shows us that it has to happen this way. The maximum of f when f is continuous on a closed interval happens at either an endpoint or a critical point of f. Now let's actually see this all come together in action here. And it comes together in the following method. So using all of these results, for given f continuous on AB, how do we find the absolute maximum value and the absolute minimum value on that interval? 4 steps. First, locate all the critical points of f. That gives you the set of candidates for the minimum and for the maximum. It has to occur either at one of those critical points or at an endpoint. So in step 2, you take all the points you found in step 1 and just put them in a list. So the list of x values that yield possible extrema of f, the critical points you found in 1 and the endpoints. Then just check the function at each point in the list, pick the biggest, pick the smallest, and you're done. And this will always work for a continuous function on a closed interval. Let's do some examples to see this. First, here we have h of x is x squared plus 4x plus 7. the interval of question is minus 3, 0. So the first thing we do to check for critical points is check where the derivative is either 0 or does not exist. This is a polynomial, so there's no problem with the derivative. Derivative exists everywhere. Setting our derivative equal to 0 gives 0 equals 2x plus 4, or minus 4 is 2x, or x equals minus 2. And one thing to note, and you always want to check this, that minus 2 does in fact fall in the interval. So we make our list. So we add 2 to the list, and that was the only critical point of f. So we need to check this minus 2, and then the endpoints, 0 and minus 3. And so plug in. F of minus 2 is minus 2 squared plus 4 times minus 2 plus 7, which is 4 minus 8 plus 7, or 4 minus 1, or 3. So there's our y value. F of 0, that one's quick, plug in x equals 0, and we get 7. And f of minus 3, we have minus 3 squared plus 4 times minus 3 plus 7. This becomes 9 minus 12 plus 7. 9 minus 12 is negative 3, plus 7 gives us 4. So we add that to the list, and it's as simple as we found the only critical point, we checked the function's value, then we checked the function's value at the endpoints, and the biggest occurs at 7. So that is our max. The smallest occurs at minus 2. So that is our minimum. So again, it's as simple as pick the smallest and pick the biggest from the list. And if we want, we can get a little bit of an idea of what the graph looks like from these points that we just found. So we know it goes through the point 0, 7. And then we have negative 2, 3. And then we have minus 3, 4. So we know our function looks something like this, and we identified that its maximum value happens here at 7. And we should be careful the way we answer this. The max value is f of 0 equals 7. And then the minimum value is f of minus 2 equals 3 here. And so when you answer these questions, you want to think of the two different things. You have the maximum value itself, and then the x at which it occurs. And the same thing here. You have the minimum of 3 occurring at an x value of minus 2. Let's look at another example. Suppose we have f of x equals x plus 4 over x on the interval 1, 4. Now, here we have to be careful. Are there any points where in 1,4 that are not in the domain of x. Is this actually continuous on 1,4? And yes, it is. The only trouble spot is x equals 0. 0 is not in this interval, so we're okay there. Let's check for critical points. Always the first step. We have f prime of x is 1. 4 over x, remember it always helps to rewrite these things. So we can write it as 4x to the minus 1. So when we differentiate 4x to the minus 1, we get minus 4x to the minus 2. Or 1 minus 4 over x squared. Setting f prime of x to 0 gives us 1 minus 4 over x squared equals 0. Or 1 equals 4 over x squared. Multiply both sides by x squared. X squared equals 4. And so that gives us x equals 2 and x equals minus 2 as solutions. So those are our only two critical points for this function. However, note that 2 is in 1,4, but minus 2 is not. So because minus 2 is not in 1,4, we exclude it. So that's a key thing to note. You always want to think about your critical points as to whether or not they're actually in the interval that we're working with. So remember our list, the way we do these. So we have our x and then our function value. We just saw that 2. We have a critical point at x equals 2. And then we throw the endpoints in. And those are the only possible points at which f can have its minimum on 1,4 or its maximum on 1,4. So once again, we evaluate at each point. F of 2 is 2 plus 4 over 2, or 2 plus 2, or 4. F of 1 is 1 plus 4 over 1, or 5. And f of 4 is 4 plus 4 over 4, also 5. And we see in this case, the minimum occurs at x equals 2. So here's our min. And our maximum occurs at 2 points. It occurs both at x equals 1 and x equals 4. So if we were to draw this, and we still have to learn a little bit more math before we start really sketching functions, but we see here that this function has its minimum value at 2, 4. And again, remember, we are restricting to the interval 1, 4 here. So on that interval, the minimum occurs at this point at x equals 2. We have a min value of 4. And then we have maximum values at x equals 1 and x equals 4, the endpoints of 5. So our function looks something like this on that interval. Let's do one more example, which will be a more challenging example. And this is an example that we've actually already seen before. G of x is x times root 4 minus x squared on minus 1, 2. And we can note right away that the domain of this function, we need what's under the square root side to be positive or non-negative. So we need 4 minus x squared to be greater than or equal to 0, or x squared to be less than or equal to 4. And that gives us the interval minus 2, 2. And we see that minus 1, 2 is inside of there. So we're not looking at quite the whole domain. So this is just a check that everything is fine with this interval. Now, critical points, our first step. We need the derivative. And we should probably rewrite g of x. This is x times the quantity 4 minus x squared to the 1/2. And so to get this derivative, we require use of product rule. So first, x times the derivative of the second, which is chain rule. Bring the 1/2 out front, leave the inside alone, reduce the exponent by 1. So we get 1/2 quantity 4 minus x squared to the minus 1/2 times the derivative of the inside function, which is negative 2x. The second term from product rule, we have the second term plus 4 minus x squared to the 1/2 times the derivative of the first, which is just 1. If we clean this up a bit, we see this 1/2 and this 2 cancel. Here we have x times x with a negative. So that gives us a negative x squared, and we can put that root term in the denominator. And for the second term, we have root positive root 4 minus x squared. So there's the expression for our derivative. Now note first, we have a problem with the derivative at any time where this is 0, which occur at x equals 2 or minus 2. So f prime of x does not exist at x equals 2 or x equals minus 2. Minus 2, that's not in our interval. So we ignore. X equals 2 is in our interval, but it's already an endpoint, so it'll be included. The other check for critical points is where g prime of x equals 0. So that's this expression being equal to 0, or root 4 minus x squared equals x squared over root 4 minus x squared. So this is just a result of setting this to equal 0, and then adding this term with the minus sign to both sides. Now multiply both sides by root 4 minus x squared, and we get 4 minus x squared equals x squared. Right, multiplying by root 4 minus x squared on the right cancels this term in the denominator. Multiplying by root 4 minus x squared on the left results in 4 minus x squared. Add x squared to both sides. 4 equals 2x squared. X squared equals 2, which gives us x equals root 2, and x equals minus root 2. So we note that we now have 3 critical points. X equals root 2, x equals minus root 2. We should be more careful. Root 2 is about 1.4. So what do we note about minus root 2? It also is not inside the interval. So negative root 2, and this is some notation. If we wrote it this way, that would mean that negative root 2 is inside, is an element of minus 1, 2. But specifically here, it is not. So when we write it this way, this is read as negative root 2 is not inside the interval minus 1, 2. So we omit. So this leaves us with, we omit this minus root 2. We have root 2. We have 2. And then we also need the endpoints. So we better include minus 1. So now we go to the next page and we draw our list. So we said root 2, 2, and minus 1. And we evaluate the function. So f of root 2 is root 2 times the square root of 4 minus root 2 squared, or root 2 times root 4 minus 2. This is root 2 times root 2, or 2. When we evaluate f at 2, we get 2 times the square root of 4 minus 2 squared. And we see that that's 2 times 0, or 0. And then when we evaluate f at minus 1, we get minus 1 times the square root of 4 minus 1 squared. Or under here we get 4 minus 1. So we get negative root 3. And we can now see from our list that the maximum is occurring here, a maximum value of 2 at x equals root 2, and a minimum value of negative root 3 occurring at x equals 1. So if we want to draw this, we had our max value occurring at the point root 2, at x equals root 2. And we have a y value of 2. So there was our max. Our minimum value was occurring at x equals negative 1, and it was minus root 3. So down here, we have this minimum value. And we plotted some other points. At x equals 2, we see that the function's value was 0. And we can also see it goes through the origin, because if you plug in 0, you get x equals 0, you'll get y equals 0. So we also can see that we get it going through the origin here. And so we know our function looks something like this. And so we see the maximum value occurring here at the point root 2, 2, and the minimum value occurring here at the point negative 1, negative root 3. Again, this is a very standard approach to these types of problems. If you follow this method, finding the max and the min values of a function that's continuous on AB, closed interval AB, this will always work. Find the critical points, which means where does the derivative equal 0 and where does it not exist. Throw those x values into a list, add the endpoints to that list, evaluate the function at each point in the list, pick the biggest, pick the smallest. We'll move on further than this, learning more about graphing functions. So we will deal with the math in this section a lot more going forward. And eventually, pretty soon actually, we'll be able to graph functions pretty effectively on their entire domains. So that's what's coming next.